Hey guys, 5.2 day 2. Start out, pause the video, take a look at this warm-up problem, and resume the video when you're ready to see the answer. Alright, so we're rewriting this where it isn't a fraction. This is a review of 5.1. This one's got kind of an unsatisfying ending. The answer to this doesn't seem like it should be all the way simplified. It seems like you should be able to do more with it, but it's not the case. And it's really this key word, expression that isn't a fraction, that's the hint as to what the right, when you have the right answer. All right, so looking at this, I've got tangent and I've got secant. Those are both pretty closely related with the Pythagorean identities, so I'm not going to start out by changing them to sine and cosine. But what I will do is, I notice that I've got secant minus 1, so I can multiply the top and bottom by the conjugate and start simplifying the denominator. Really, if I'm expressing this where it isn't a fraction, having two terms in the denominator is kind of a problem. If I can get this down to one term, that's going to make this a lot easier. So multiplying by the conjugate, secant plus 1 on top and bottom. Numerator, I'll distribute in tangent, and I'll get secant tangent plus tangent. And in the denominator, when I FOIL these two out, it is secant squared minus 1. If we look to our Pythagorean identities, the Taylor-Swift one, if I subtract 1 from both sides, I get that tangent squared is equal to secant squared minus 1. So this is secant tangent plus tangent all over tangent squared. Now, both terms in top have tangent. There's tangent on the bottom, so I can start canceling some stuff out. One tangent from the bottom is going to cancel one of each. So that's going to leave, on the numerator, secant plus 1. Remember, when that tangent cancels out, it doesn't just go away. It's a 1 over tangent. Now, I haven't gotten this to not be a fraction yet, but what I have done is I've made the denominator into one term, and that also made the numerator into two terms. But that's actually not a bad thing, because the next step, I'm going to be able to start making these things not be fractions anymore. All right, so what I can do is I can split that numerator apart and make it secant over tangent plus 1 over tangent. All right, so this side, I can already make that not be a fraction by making it cotangent, right? So good, I've got half of this done. Now over here, I can't immediately simplify this any further, but if I change things to sine and cosine, maybe that'll help. So secant is 1 over cosine, tangent is sine over cosine. Now I can do keep change flip with this, 1 over cosine times cosine over sine. The cosines cancel out, so I'm left with 1 over sine. 1 over sine is cosecant, so this is cosecant plus cotangent. And where this is sort of unsatisfying is that it seems like this should be able to be simplified further, but the only things that I can really do with this would cause it to become another fraction, which isn't the goal. The goal is to try to make it not be a fraction. All right, so second day of 5.2. We're going to cover a little bit of the Santa Claus, Taylor-Swift, Captain Crunch stuff, why that stuff works the way it does, and then 3 examples. 2 of them are pretty quick, and it's just to highlight a couple of strategies that I weren't in the previous video that you'll need, and then one just sort of difficult problem just to see a really tough one. All right, so Santa Claus, Taylor-Swift, and Captain Crunch. Where does this stuff come from? We're going to start out here. Why does sine squared plus cosine squared equal 1 in the first place? If you think back to the unit circle, if I make a unit circle and I put some random angle on their x, I know a couple of things right away. I know if it's the unit circle that hypotenuse is 1. I know for every angle, I can make a triangle, a right triangle. The adjacent side is equal to opposite over hypotenuse. Sine is equal to opposite over hypotenuse. And so if the hypotenuse is 1, that means that this side is just equal to sine of x, because it's sine of x over 1. It just stays sine of x. Same thing with the adjacent side. It's adjacent over hypotenuse is cosine. That means that if the hypotenuse is 1, that adjacent side is equal to whatever cosine is. Well, now I've got this right triangle where it's sine of x and cosine of x, and the hypotenuse is 1. The Pythagorean theorem says that a squared plus b squared equals c squared. So sine squared plus cosine squared equals the hypotenuse squared, which 1 squared is just 1. So that's why this is a thing, and why we call it a Pythagorean identity. All right, now where do the other ones come from? Where Taylor Swift and Captain Crunch come from? Again, this isn't a static equation. It can be manipulated. If I start by dividing everything by cosine squared, so I haven't changed the value of anything, right? I'm keeping things balanced on both sides of the equation. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. Well, that's the Taylor Swift identity. If I do the same thing with sine, I get the Captain Crunch one. Sine over sine is 1, cosine over sine is cotangent, and 1 over sine is cosecant. So not 100% necessary that you understand that to be able to succeed on the assessment for this, but it's worth knowing why it's a thing, that it's not just something to believe because I said it was true. Okay, so first example. If you want to pause it now and give it a shot on your own, do so, and then unpause it when you're ready to see how it's really done. Okay, so if you're looking at this, if you're trying to use a Pythagorean identity for this, the numerator, it's understandable, but it doesn't work, and here's why. 1 plus cotangent squared equals cosecant squared. I can't make one side of this equation equal to cotangent squared minus 1. I kind of can, but if I start out by maybe subtracting 1 from both sides, I get cotangent squared equals cosecant squared minus 1. Well, that doesn't quite work. It looks sort of like it, but cotangent's on the wrong side. So maybe I subtract another 1, and I get cotangent squared minus 1 equals cosecant squared minus 2. Well, I guess technically I could replace this with cosecant squared minus 2, but that doesn't really help anything. It's not going to get me any closer to my answer. What I really need to do here is factor. This is a difference of squares. If it were x squared minus 1, more of you would recognize that you could factor it to x minus 1, x plus 1. Well, I'm going to do the exact same thing, except instead of x, it's cotangent. So cotangent minus 1, cotangent plus 1, all over cotangent minus 1. Well, look, I've got two factors that can cancel out, and what I'm left with is cotangent plus 1. So pretty quick one if you know how to start it. All right, next one, same idea. If you want to pause the video, give it a shot. I'm going to show starting by splitting this fraction. So if you want to try it that way rather than using a Pythagorean identity on top, and see if you can come up with the right answer. Okay, so again, I can split a fraction. That's going to be something that's going to pop up in the homework, so it's worth knowing how to do. That's why I did it in the warm-up, and I'm doing it here. So if I start out splitting the fraction up, again, the denominators are the same, so I could recombine this and make it back into this fraction, so that's allowed. These are equivalent forms. Now I can start doing some simplifying. These signs would cancel out 2 from the bottom, so I'm left with 1 over a single sign. And then over here, it's 1 over sine cubed. Well, that doesn't really go anywhere. I can change this to cosecant. And then 1 over sine is cosecant here, so this would be cosecant cubed. Well, now I've got something that I can factor again, right? Because if this were x minus x cubed, I could see that I've got a GCF there. I'd factor out an x. Same thing. I'm just factoring out a cosecant. So cosecant times 1 minus cosecant squared. This is a Pythagorean identity. It's not equal to cotangent, though. And if you think about it, it has to be negative cosecant cotangent squared. So that's a little hint as to what the next step should be. So if I do 1 plus cotangent squared equals cosecant, to get one side to equal 1 minus cosecant squared, I'd have to subtract the cosecant squared from both sides, but then also subtract the cotangent squared from both sides. So that cancels, I'm left with 1 minus cosecant squared equals negative cotangent squared. So this is equal to negative cotangent squared. And now all I'd have to do is move that negative out in front and get rid of the parentheses to make it look like this. So we'll call that done. All right, last example. Now I just found one that is pretty complicated. I wanted to just make sure to show one really nasty one. So if you feel good about this, you want to give that a try, pause, and come back when you're ready to take a look at it. Okay, let's see. I'm going to do a little bit of work on this side first. I'm looking at this, and I'm thinking, I've got tangent and cotangent. They're not related with Pythagorean identities. So, and then I've got cosine over here. So I'm thinking this, I'm probably leaning towards changing it to sine and cosine. Over here, I think I'm going to split the fraction up and just see, and just break this side down a little bit and see what I can do with it. This is the more complicated side, so I'm going to focus more on this. But I think I'm going to try to simplify this side a little bit to give me a better goal to shoot for with this side. So if I split the fraction up here, I've got cosine squared over cosine squared minus 1 over cosine squared. So that cancels, becomes 1 minus 1 over cosine is secant, so 1 minus secant squared. And 1 minus secant squared, that looks like a Pythagorean identity, but let's check. Tangent squared plus 1 equals secant squared. So again, if I subtract the secant and the tangent, what I'll get with is 1 minus secant squared is equal to negative tangent squared. So this can be thought of as negative tangent squared. And, I know that I'm going to end up at some point converting all of this into sine and cosine, so I'm going to convert this to sine and cosine as well. And so now I'm really trying to make this fraction look like this fraction. And I think that's going to be a little easier than trying to make this not be a fraction and get it to equal tangent squared. It's certainly easier than trying to make it equal this, more complicated fraction, more complicated than this one. Okay, this side, if you're thinking Pythagorean identities, that's a good way to think, but if you check, you really can't make them equal. So if we go back over to the Taylor Swift one, I can't get this to be 1 minus tangent in any useful way. And the same thing with 1 minus cotangent squared. It's 1 plus cotangent squared equals cosecant squared, and so I can't move things around to get this side to equal to 1 minus cotangent squared. So what I'm going to do instead is change everything to sine and cosine. So tangent is sine over cosine, cotangent is cosine over sine. Now I've got kind of a mess of a fraction on top and on bottom. I'm going to try to get this to be 1 fraction on top and 1 fraction on the bottom. So I'm going to make a common denominator with the 1 by multiplying by cosine over cosine. Same thing on the bottom, except sine over sine. And so now I'm going to get cosine squared minus, for the numerator, minus sine squared all over cosine squared. And the denominator will be sine squared minus cosine squared all over sine squared. It's still pretty complicated, but at least I've got one fraction over one fraction, so I can use keep, change, flip, and just see if that's going to help break this thing down a little bit. Okay, and I'm going to have to move it over here now. So, cosine squared minus sine squared over cosine squared times, changing that to times and then flip the bottom, to sine squared over sine squared minus cosine squared. Now looking at this, the cosine and the sine here don't cancel, but I've got this cosine minus sine squared and the sine minus cosine squared. Those almost look like they could cancel, and they're really close, but if I notice, like, the sine is the wrong sign, and the cosine is also the wrong sign. It's positive here, negative here, the sine is negative, and then positive. So if there were a way that I could, like, switch the signs of one of these, I could get them to match and they could cancel out. Well, I can do that by factoring out a negative. So I'm going to factor a negative value out of here. That's going to make sine positive and cosine negative. Well, now I've got sine squared minus cosine squared and sine squared minus cosine squared. Those can cancel out. Now, if you're wondering how I did that, right? I didn't change the value of anything here. If I distribute that negative back in, then it's negative sine and positive cosine again. This would be a negative sine, that would be a positive cosine. So all I did was I factored out a negative and reorganized them. I just switched them around so that they would look the same. All right, so now I can cancel here, cancel here. I've got a negative and a sine squared on top, so negative sine squared, and I've got a cosine squared on the bottom. Negative sine squared over cosine squared, that's what I came up with on the other side as well, so you can call that one done. All right, here is your homework assignment. And again, make sure to check out the homework help videos. I've got 3 videos that go through, each one goes through 2 or 3 of these, about 5 minutes long, to help you guys out.